Okay. And the third one, beanbag is carried across the room at constant speed. So here goes the beanbag at constant speed. We should talk about this. What are the at constant speed? So after I've gotten it started, okay, not the getting it started. While it's moving at constant speed, what would the free body diagram look like for the beanbag?
And you'd have force of friction, wouldn't you?
Well, there's no friction, it's just gravity and normal force.
All the forces would have to be balanced at its constant velocity, right?
Mm-hmm.
There's no sideways forces at all.
Well,
No sideways forces
Well,
at
there
all?
kind of are, but that would be part of your arm, not your hand. So, like,
on the beanbag, this is our object,
there's
just the
friction between
beanbag.
I thought it was the
hand,
hand
right?
of the beanbag. So it's just the beanbag moving.
Force is
the
just on the
friction is
beanbag.
only as strong as the force that's propelling it in the opposite direction. And
Well,
that
there's-
force is
there's
zero in this
friction.
case.
Like, because if there wasn't any friction, then it would just slide off your hand and stay there.
But
Okay,
it
so
already has some momentum.
Which moment is he talking about?
Or like any moment.
You're talking about the
When it
moment when I'm
starts?
getting it started. Yeah, and to exaggerate, right? If I start my hand, I'm doing it so slow you can't really notice that I'm doing it so slow that there's enough friction to get the beanbag going. But if I did it fast enough, right, there wouldn't be enough. But so there needs to be friction to get it started moving. That's what actually starts it moving, like when you walk, right? But it's already moving now.
So just up and down.
So,
Like just up and
Normal
down.
gravity.
so I guess it's friction pushing that way. Like, I'm
What?
not quite sure what's pushing that way to counterbalance going that way. Like,
There is no forward force once it's already started.
oh, okay.
Seems weird, doesn't it? But there's no forward force once it's already moving. To get it moving, I have to push this way on it. And then to stop it, there would be a sideways force. But constant velocity, there are no sideways forces. So we have upward force of the normal force, downward force of gravity. Are any of those external forces?
That would force normal.
The normal force is an external force. Does the normal force act through a displacement?
No.
The object has a displacement, and this chart is it could be a little confusing. Go ahead and draw an arrow to the right that the displacement of the object is to the right. But the force doesn't actually
The force is upward.
act through that displacement. The force is upward and the displacement is to the right. When you have that situation, did the energy of it change? So it's going at constant velocity.
No.
No, the energy is staying the same. It's not speeding up, it's not slowing down, it's not going higher, it's not going lower, so the energy stays the same. So the only time you get a transfer is when the force is in some sense parallel to the displacement. Okay? There's a name for this whole thing, that when an external force acts through a displacement. Any idea for what that kind of transfer is called?
Motion?
No, good question. Good guess. It's called doing work. It's called work. So when a force acts through a displacement, we say that that force did work. Okay, part B. Another way to transfer energy. The mug, I put it in the microwave. What happened in the microwave?
Energy was transferred into the...
How?
How does the microwave work?
How does the microwave work? Is it
How
molecules?
did energy get transferred into the water?
Vibrations, I guess. Like heat.
What?
the
Yeah.
molecules
What
actually
came
hit
in
the
here?
surface
That
of the water.
what came in here to
Heat.
make the molecules vibrate more?
Heat.
Heat.
Well, the
The
energy...
molecules moving very
Heat.
fast, actually.
Heat. Does the microwave generate heat inside?
No, it just moves molecules around. Doesn't that generate heat?
It made the molecules move around, which made the water increase in temperature.
Doesn't that also
I guess
increase the energy?
I guess it made the molecules move using the microwaves.
Yeah, the microwaves. What are microwaves? Microwaves.
Oh, I don't know. Wait,
Microwaves
I don't know
are
microwaves now.
a form of light, just not light that our eyes are sensitive to. So it's just exactly the same thing as light. It's called electromagnetic radiation. Same thing as light, but you can't see it just because our eyes are designed to pick up only certain wavelengths of light. So microwaves, which are radiation, electromagnetic radiation, come out of the thing in the microwave. I think it's the magnetron. Anyway, something in there makes the microwaves. And they get absorbed by the water molecules. And when they do that, the energy from that radiation makes the molecules move faster. So this one is radiation, and that's the same way that, so part B is radiation. Example is microwaves, how they use the energy from the microwaves to warm things up. But also the sun, that's what we're receiving from the sun. We receive energy from the sun by radiation.
Solar panels.
What?
Solar panels.
Yeah. Part C, here's another one. Suppose you have a lawnmower or a car, and what do you have to put in it in order for it to operate?
Gasoline.
Gasoline. So you have your car, and you put some gasoline into the car. What have you done now to the energy of the system? If the system is your car, does it have more energy after you put the gas in it?
No. Well,
Assuming the engine's on?
You can turn the engine on.
Does it depend whether or not the gas is about the system?
The gas is not part of the system. So the system is just your car. Now you're going to put gas into the car. Once it goes in there, it becomes part of your system.
Then I guess it increases.
It increases because does the gas have energy?
yes.
It does. It has chemical. We haven't talked about that. There's more kinds of energy than just these four.
Oh.
Chemical potential energy. But
Oh, no.
what that is, when we do that, it's called mass transfer. Same thing if I take a bite of a sandwich, right? If I'm the system and I take a bite of a sandwich, right? I now put something, I put actual mass, I put some kind of object in me that has energy. Food has energy.
Is food chemical? Oh,
Chemical potential. Because of the bonding of the
So whenever you
And that's why
transfer
you
mass,
burn
that's
it.
also a form of energy.
What?
Whenever you transfer mass, that's also a form of energy. Basically.
So there's the ways of storing energy, and then there's the ways of transferring it, which are two different things. These are ways of storing it, and we could have one more that says chemical potential. Transferring it is how did it get from outside the system into the system. So storing it, we could have, let's say this is chemical potential here. Let's say this is just me. I'm the system right here. And this is, this right here is the sandwich. My analogy might break down. We'll find out. This is chemical potential energy. But this is outside the system. If we take the actual sandwich and we move that mass into me, we've now moved energy. But we did that by moving the mass.
Oh, okay.
You can either move mass, like put gasoline from here to there, or you can put a force through a distance, or you can put radiation into something. Those are all ways of moving energy from one place to another.
Okay.
That helps. It's all very
Got
abstract.
a bit sidetracked
Hopefully it'll start to solidify. Okay, part 6, and then we're almost ready to do our lab. Part 6, what happens when internal forces act in a system? Okay. I'll write this down and then we'll talk about it. When internal forces act, forces that act between objects in a system.
Where do we write this?
In
Number 6.
Oh, what was C? Chemical?
Chemical. Yeah.
B was radiation and C was mass transfer.
Oh.
Sorry. I'm glad you asked. Chemical potential energy would go in that chart up above if you wanted to add it. It's another way of storing energy. It's not actually a way of transferring it from one place to another. You could compare it to bank accounts. My bank accounts are the ways I store it, but the ways I transfer it are I go to an ATM, or I walk into the bank and I say, give me my money, or I drop a dollar bill on the road. Those are ways that I transfer money. But the actual accounts are the ways that the money is stored. Forces that act between objects in a system will cause the energy storage modes to change.
Snapped. forces come from?
Okay, forces that act between objects in a system. What do we call those kinds of forces? Are those internal forces or external forces?
External.
Forces that act between
Oh,
objects in
internal.
a system. Those are
Thinking
external.
internal.
Okay, so these are internal forces. So when internal forces act, we will have a change in how the energy is stored, but not in the total energy. So when internal forces act, you're just moving things from one category to another, like from one bank account to another one. And here's an example. Stick with me, Mark. You can do it. What are you doing? Impaling things?
No, the other Mark shot him with the bow at the air.
Okay, so in situation A, we have the beanbag. When I release the beanbag and it's falling, what force, so here's B, right when I've let go, it hasn't started moving yet, but I let go. What force or forces do we have on the beanbag at the instant I have let go?
Force
Gravity.
of gravity.
Force of gravity. And what about here when it's fallen partway down?
Gravity.
Still just gravity.
Force of gravity. And here at the instant just before it touches the floor,
Still
still
force
force
of
of gravity.
gravity.
Is that an internal force or an external force?
It's internal.
Internal.
And it's an internal force. That means that as the beanbag falls, its total energy of the system does not change. But you say, it has less gravitational potential energy. How could the total energy not be changing?
Wait, what?
So as it falls, is the gravitational potential energy decreasing?
Yes.
But what else is happening?
The potential and the kinetic energy is
The
increasing.
kinetic energy is increasing.
We have kinetic in there?
Not here, because it's not moving.
Oh.
But what about partway down?
Okay.
It has kinetic and gravitational. Okay.
So
So
in our pie chart, we probably should have written out the kinetic energy at 0. Because it's going to be involved later.
No, because it doesn't have any slice of the pie, because there's none here.
So 0. So
You could write out here
Okay.
EK is 0 if you want to.
that might be less
So let's
confusing
draw
to
a
do.
pie chart now for these two. Okay, we're going to draw pie charts for lots of different times. Make the size of the circle exactly the same. Because there is no external force acting through a displacement to cause a change in the system energy. Okay, what's happening here is, here's my little buckets. Gravitational potential. Here's my kinetic energy storage mode. Kind of like little accounts. Elastic potential energy and internal energy. So initially, we had all gravitational potential energy. That was at point B. At point B, it was all gravitational potential. Now we have an internal force. Internal forces move things from account to account. They don't take things out of the system, they just move them around inside the system. So my internal force, halfway down, we have less gravitational, but now we have some kinetic. So the size of it's the same, right? There's still $1 in there. But some of it is now kinetic. We have less gravitational. You can see that the piece of the gravitational is smaller. But the kinetic has increased because it's now moving.